All right, so welcome to Math Stat 341, Probability. This is lecture 13. We are going to be discussing today joint PDFs, linearity of expectation, one of my favorite techniques. We'll give some applications, to estimation problems like Fermat primes and Buffon's needle, which is a great way of doing a problem multiple ways. The big item for today is to see the power of linearity. So the expected value or the mean of a sum of random variables is linear. This is not the case for the variance. And this is why a lot of calculations, it's much easier to work with the mean. We will also see, or at least you'll see if you read some of the additional material, that you can often avoid very painful calculations by cleverly looking at the problems. And just to have things established for the record, I did mention a few days ago that it might have been strategically better for the Red Sox to have to play the wild card game and the playing game, to have their pitching rotation set up better to maybe lose game one and then be in better shape for games 2 and 3. I'm just stating that for the record. No comments about what will happen now. All right. So I will just put this in the slides just for completeness. The advantages, of course, this is all in the book. These are also on the slides. A lot of times I just want to do this so that the material is just easy to find. So, the joint probability density function. So let's assume we have random variables x1 through xn. And then, we can do them as continuous, or we can do them as discrete. More generally, you could do them as a mix. I like writing integrals more than I like writing sums. We have better formulas for integrals than sums. So normally my go-to is going to be to write things for integrals and continuous. You can, of course, do this similarly for discrete. And it's the probability that I have a tuple of random variables giving me, some value. How would I define this? And so there's a lot of different ways to do this. We're going to see the convolution function in a moment, but this is giving me the joint probability distribution of this pair. So I have to give you some function. So notice, I'm not saying whether or not my random variables are independent or dependent. So if I roll a fair die and it comes up a 4, can you give me a random variable related to that die roll that is going to be completely dependent on that? There's 2 natural ones. So that when you roll the die, you have a 4 on the top. I'm sorry? Well, I'm just doing one die roll. I just roll one die and I have a 4 on top. Give me something related to that die that's completely dependent on 4. There's 2 natural answers. I'm sorry? I'm sorry? Okay, so so that will be dependent on, that will be completely correlated to the 4. So if I roll an even number, it's got to be even, sure. Other ones, it's not 4. I was thinking the number on the bottom, right? What's the number on the opposite side of the die from the 4? 3. So you always have the number that adds up to 7 on the opposite side. So one possibility of a completely dependent random variable would be the number on the bottom of the die. And so what I might be able to do is I might be able to give you just some function that depends on the x1 through xn. And the more complicated the function is, the harder it's going to be to say anything good. What would be beautiful is that if the density function actually factored as a product of functions. And that's going to be the case if it's independent. So we're independent if the joint density function can be written as a product of the densities of each one. Well, I may not initially give you the densities of each one. You might have to figure out what they are. Well, imagine I want to figure out what is the density of the random variable xi. What I do is I hold xi fixed at some particular value. So you use lowercase xi to represent that value. And then I take every other random variable and I integrate everything else from negative infinity to infinity. And so as I do everything else from negative infinity to infinity, I'm looking at, look, all I care about is look at every tuple where the value of the ith one is little xi and integrate over everything else. And that will give me the density function of just the random variable xi. So we often call these the marginal densities. And of course, if I just integrate this now from negative infinity to infinity, I would be integrating everything from negative infinity to infinity, and what would I get? So what would I get if I integrate this from negative infinity to infinity? I would just get 1. It's a probability distribution. The integral over the entire space is just 1. This is the probability that my tuple is an S. If I have S be all of Rn, that it's somewhere, it has to integrate to 1. This is clearly going to be non-negative because I have a non-negative function and I'm integrating it over a region. So it at least is a good candidate for being a probability distribution. So the book goes through and it does, some examples of, the joint density. There may be some typos in the book where, we could look at, X is the number of heads in the first 3 tosses, Y is the number of heads in the last 2 tosses of 5 independent tosses of pair coins. And so in this case, the 2 random variables are independent, and we get a nice little chart like this. In the second one, we have the joint density. We use the number of heads in the first 3 tosses, and V is the number of heads in the last 2 tosses of 5 tosses of fair coins. And so I'm not saying here that they're necessarily independent tosses. And so if they are independent random variables, then the probability of x1, x2 is the probability of x1 times the probability of x2. How do I calculate the probability of something? Well, if I want the probability that y equals 0, I just add everything in that column. Because I don't care what x is, I just care what y is. I just care that y is 0. So I look at, this is when x equals 0 and y equals 0, x equals 1, y equals 0, x equals 2, y equals 0, x equals 3, y equals 0. So I get 1/4. And if it's independent, then the probability that y equals 0 times the probability x equals 0 should be the probability that x equals 0, y equals 0. And we see for the first one that it does match. So 1/4 times 1/8 is 1/32. You can go through and check all the other ones and everything works out. There's not that many things to check here. You can do it, or even better, you can train your computer to do it. For the second one, is this independent? Is the probability of u comma v the probability of u times the probability of v? Okay, which one do you want to check? Okay, why u1 v2? So we have 2/16 and we have 3/8 times 1/4 is 3/32. So it does not work. To me, there's a more natural one to check. That works. Yeah, 0, 0. So you have 1/16, you have 1/4 times 1/8. But I find there's an even better one to check. The 0/16. Yeah. I see over here immediately I've got a 0. So as long as the two things aren't 0, I know their product can't be 0. Again, it doesn't matter. Any one of them that you check is going to be enough to show that these are not independent. And so what might have been going on here is I might have had it so that the last 2 tosses might have been related to the first 2 tosses or something like that. Okay. So what I want to do now is I want to talk about one of the most useful things we can do in probability. It's called the convolution. And you can do it for integrals and you can do it for sums. We do it more often for integrals just because things are a little bit nicer. And so we have, random variables x and y with PDFs f of x and f of y. And let's let z be x plus y. Assume the random variables are independent. If the random variables are not independent, it is extremely hard to study the sum of x plus y. We could have the special case where x equals y, in which case x plus y is just going to be 2x. Or you could have y equals negative x, in which case x plus y is always 0. So if the random variables are allowed to depend on each other, if I take a symmetric distribution, x and negative x have the same density. I can't tell the difference between x plus y in these cases. So we don't want to, I mean, we'd love to study dependent random variables, but it's much harder. We will study the case when X and Y are independent random variables frequently. Are independent, and we'll say the density is going to be F sub Z. And we want to figure out what can we say about F of Z. We've already done this a little bit. When we roll the fair die, we get the numbers 1 through 6. We get a uniform distribution. Each number occurs as often as any other. If we sum two fair die, we got a triangle distribution. 7 occurred 1/6 of the time, going all the way down in probability to 2 and 12, which only happened 1/36. So I claim that the density function of Z is the integral from -infinity to infinity of fx of t fy of z minus t dt. If you think about this, this is reasonable. Why is this reasonable? Well, we want x plus y to equal little z. If x equals t, we need y to equal z minus t, integrate over all x. So this is a really nice, quick, 10-second justification of the convolution. Here's a better one. My internet connection is unstable. Oh, but it's not displaying that to you, it's only displaying that to me. So the probability that big Z is less than or equal to little z, this is the cumulative distribution function of big Z. Okay, so it really was correct that my internet connection is unstable. Wow. Oh, this could make it interesting. Okay, now, this is the installment plan. Like, anybody ever see the old Franklin Mint commercials? You get one piece every other month. My famous was the chess of the Civil War would actually take longer to get all the pieces from the chess set than the Civil War took to fight. All right, so the probability that big Z is at most little z, that's the cumulative distribution function. All right, so how would we calculate what this is? So this would just be the integral over fx of x, fy of y, dy dx, and we want x plus y to be less than or equal to little z. So if we integrate over all pairs where x plus y, so if we integrate over all pairs where x and y add up to at most little z, then this is going to be the probability that big Z is at most little z. All right, so how can we do that? Well, this is the same as the integral x goes from -infinity to infinity. And so now, if x goes from -infinity to infinity, how large can y go up to? So we want x plus y to be at most little z. How large can y get? So we want x plus y to be at most little z, not z minus infinity, not z. I want x plus y to be at most z. If I give you a value of x, how large can y be? Z minus x, right? Y can get as large as z minus x. If y was larger than z minus x, then I might be going too far. Imagine y was equal to z plus 5. Well, if y is z plus 5, and I add x, well, maybe I'm okay. maybe z plus 5 plus x is at most z, but that will only be the case if x is negative 5 or smaller. I have to make sure that when I add x and y together, that the result is at most z. So the range for y goes from minus infinity all the way up to z minus x. And then I would just have my density as before. And so I would have my density function fx of x, fy of y. Which integral do you want to do first, the x integral or the y integral? Yeah, because if I do the y integral doesn't depend on anything. And so when I integrate that, I will get the antiderivative. And so I'll get the antiderivative evaluated at negative infinity and z minus x. And then, of course, I'll have to then do the resulting x integral. So now I have my cumulative distribution function and I evaluate it at z minus x and negative infinity. What do I get when I evaluate it at negative infinity? I get 0. So it's just my cumulative distribution function evaluated at z minus x. It seems to be a little bit cut up. So this is the cumulative distribution function of z, is this integral. How do I find the density given the cumulative distribution function? What do I do? How do you get the density from the cumulative distribution function? What's the relation between the two? To go from the cumulative distribution function to the probability distribution function, we take the derivative. So it's just going to be d by dz of big fz of z. And now we wear our physics hat or our engineering hat. What's the derivative of an integral? Right. Do we have to justify that? If you're wearing your physics or engineering hat, no. If you're wearing your stats hat, I'm not going to answer that question. If you're wearing your math hat, absolutely. And that's why we have classes such as real analysis, where you will justify something like that. I remember my freshman physics professor once said, the following step takes 6 weeks to justify in mathematics. Moving on, we see beautiful twinkles. So you have to justify saying the derivative of the integral is the integral of the derivative. So using real analysis, this is the integral from x equals minus infinity to infinity, fx of x. Now, when I bring the derivative inside, what's the derivative of the cumulative distribution function of y at z minus x? So what's the derivative of the cumulative distribution function of y? It's little f of what subscript? Little f of y at z minus x, and then we need the derivative of z minus x with respect to z. And this is the chain rule. Well, what is the derivative with respect to z of z minus x? This is just 1. And there's the proof. So that proves the claimed formula that we had, I think, from the previous page. Oh, it's the top over here. Fx of t, fy of z minus t dt. The only thing is I used the letter t rather than the letter x. Not a big deal. So this is a beautiful proof. One of the things I absolutely love about this proof is whenever you integrate, you should be afraid, because integration is hard. I have just found out that I'm going to have to teach Calc 2 next semester, which means my entire career of avoiding Calc 2 will come crashing to a head. And so I will finally have to teach people how to integrate. Every other class I've done, I actually teach people how to integrate without integrating, which I will show you later. Whenever you see a capital F, you should be very worried. But fortunately, we have a capital F, and then we immediately differentiate. This is a good suggestion as to why we should be taking the derivative. Because whenever we see a capital F, we're terrified because we can't integrate in closed form most functions. So this is the CDF method. This is calculating. Now, there's a lot of things we can do from this. We write F star G of Z is the integral from, say, t equals minus infinity to infinity of F of t G of Z minus t dt. I claim F star G equals G star F. The convolution of F and G is the same as the convolution of G and F. One way to prove this is change of variables. So proof 1. Change of variables. There's a better proof though. Proof number 2, if F and G are densities of independent random variables, then what is F star G? Somebody give me an interpretation of what F star G is if F and G are densities of independent random variables. But there's an interpretation. If X and Y were independent random variables and Z is X plus Y, we just showed the density of Z is the two densities convolved. So F star G is the density of X plus Y. However, yes. However, G star F is the density of Y plus X, which equals X plus Y, so must be the same. As addition is commutative. Anybody know who Tom Lear is? Mathematician and Saros? So we have Y plus X is X plus Y. So we don't actually have to go through the change of variables. We know F star G is the density of the sum of two independent random variables. G star F is the sum of the two independent random variables in the other order. But since addition doesn't matter, which order you do them, they must be the same. Now, proof 2 only works if F and G are probability distributions. It doesn't work in general. So in general, the change of variable is better. But I like proof 2 for 2 reasons. One, it really highlights what's going on. And 2, what class is this again? All right, this is not a hard question, guys, right? What class is this? This is probability. So it's not unreasonable in a probability class to assume that our functions F and G are probabilities, in which case all the conditions of proof 2 are met. All right. In previous years, I've actually done an example using the CDF method to find the density of, say, X squared when X is a uniform or something like that. We already did that problem, so I'm not going to do that now. So what I want to do now is I want to mention a beautiful theorem, linearity of expectation. So let's X1 through Xn be random variables. I started to say independent and I corrected myself. They do not need to be independent. In fact, that's the entire point. Let's let G1 through Gn be functions such that the expected value of each Gi of xi exists. Then the expected value of a linear combination is the linear combination of the expected values. So what we mean by this is if x has density f of x, then the expected value of g of x is just the integral from minus infinity to infinity of g of x times fx of x dx. So very useful choices are, g of x equals x gives you the mean. G of x equals x minus mu squared is the variance, when mu equals the expected value of x. And we often write this expected value of x minus mu squared, which is the same as the expected value of x minus the expected value of x squared. And we write that as sigma squared. Whenever you define something as a symbol to a power, it is telling you that that is not the fundamental quantity to look at. So the fundamental quantity to look at is not the variance, it is the. So what do we look at? Not the variance, but the. So instead of looking at sigma squared, what should we study? Standard deviation. Sigma, which is the square root of sigma squared. And this has the same units as mean. And this is why the standard deviation is the natural quantity to study. If x is in meters, then the mean is in meters, but the variance is in meters squared. So if you wanted to guess my height, maybe a little bit generous and say 5'9", thank you. But you would never say, you're 5'9" plus or minus, 16 inches squared. If you're trying to estimate someone's height, you wouldn't be giving an area as a measurement of your uncertainty. Any Star Wars original series fans, original movies? Where in Star Wars do they use the wrong unit of measurement? But then they have to correct it later. Yes. Yes. So they talk about how the Millennium Falcon, that's the ship that made the kettle run in under so many passes. Under 12, I think. That sounds about right. How confident are you in 12?
Sorry?
How confident are you in 12?
7.
I think it is 12. Do you want to bet a homework problem?
Yeah.
All right, so we have a homework problem
I'll
bet.
do an extra.
Yep, so you get one in the bank. Do you want part of his bet? All right, so if it's right, you each have one homework problem in the bank. If not, oh boy, do I have a fun problem for you. And so a parsec is a little bit over 3 light years. It's a unit of measurement. It's not a unit of distance. When you're talking about somebody running a race, you normally don't tell people, yeah, they ran the marathon in 42 miles. Everybody else does it in 26, right? So they're saying the Falcon was such a great ship, it was able to take a route that was normally too dangerous for others. All right, so this is linearity of expectation. And so the question is, how do we prove this? So we want to prove the expected value of, say, a sum is the sum of the expected values. And I'll do it in a special case when we have just a sum of 2 random variables. You can then generalize this to the case where we have a more general linear combination. Well, let's let z equal x plus y. So the expected value, we having trouble again? Oh, sorry, thank you. I can fix that, but for the other one, I do need the eraser. Well, I mean, what I wrote was at least correct. And so, you know, in terms of errors to make, it's at least not a horrible error. So the expected value of x plus y is the expected value of z. This is going to be the integral from minus infinity to infinity of z times fz of z dz. So this is going to be the integral from minus infinity to infinity of z, and then the integral t goes from minus infinity to infinity fx of t fy of z minus t dt dz. And I'm just putting in the definition of it. Is this okay what I'm doing? Good. So this assumes independence. So this is not going to be a proof that will work in general. This is a proof that will only work in the special case when they're independent. So in that case, you know, we can write this as the integral minus infinity to infinity, the integral, so this is z goes from minus infinity to infinity, t goes from minus infinity to infinity. I'm going to write this as z minus t plus t fx of t fy of z minus t dt dz. So what did I just do? I added 0. I did nothing. So this is just adding 0. And now we don't have that many techniques for multivariable calculus. We have change of variables, and we have change the order of integration. So we could do the z integration first. So this is the same as the integral. T goes from minus infinity to infinity. And first I'm going to do like linearity. I'm going to just use, I'm going to break up the integral. So I'll do z goes from minus infinity to infinity, z minus t plus t fx t fy of z minus t dz dt. And now I can break this up into two different integrals to do. So the first is, you know, t goes from minus infinity to infinity, t integral z goes from minus infinity to infinity, fx of t fy of z minus t dz dt plus the integral t goes from minus infinity to infinity, integral z goes from minus infinity to infinity, z minus t. I can put the fx of t over here, fy of z minus t dz. And so I'm just using the integral of a sum as the sum of the integrals. When I look at this integral now, if I do the z integral, well, as z goes from minus infinity to infinity, I just get 1. Because I'm integrating my density over the whole thing. So I just get 1. And then I'm left with t fx of t, which is just the expected value of x. So the first piece is just the expected value of x. For the second piece, this is going to just be the expected value of y, because instead of having, you know, y as my argument, I have z minus t, but I have z minus t out over here. So if I just do a change of variable in that little y to z minus t, it's going to be the same thing. This will just be the expected value of y, and I just integrate my x density, and I just get the expected value of y, because the integral of x is just 1. So this is the proof in the special case when it's independent. If they're not independent, it's a little bit harder. And so let me just go through and do, if not independent, we want the expected value of z. So that's going to be the expected value of x plus y. And so we have the joint probability density function fxy of little x, little y. And that's what we have to work on. So what I would want to do is I would want to integrate x goes from minus infinity to infinity, integral y goes from minus infinity to infinity, x plus y times fx y of xy dy dx. And so I take each pair xy and I weight it by the sum. And I want to integrate this over all possibilities. So this is going to give me two integrals. I'm going to have an integral x goes from minus infinity to infinity of x, integral y goes from minus infinity to infinity of f of x, y, xy, dy, dx, plus the similar integral, and I'm going to just change the order. Y goes from minus infinity to infinity, integral x goes from minus infinity to infinity of y, f xy, xy, dx, dy. And so now when I do this, I'm holding little x fixed, and I integrate y from minus infinity to infinity. That's just the marginal of x. And over here, it's just the marginal of y. Except, I can just pull the y outside the integration. Because that's the definition of the marginal, that's the density of x. I fix the value of x and I integrate over all possible values of y. So I'm left with the integral x goes from minus infinity to infinity, x times the density of x dx, plus the integral y goes from minus infinity to infinity of y times the density of y dy, and that's just the expected value of x plus the expected value of y. And so this is a better proof. This proof does not use the independence assumption. It uses the joint probability density, and it just carefully goes through, and we constantly switch orders of integration to make things nice. You can, of course, generalize this proof, and instead of x plus y, I could have g1 of x plus g2 of y. And so it's a nice exercise. Go through and prove this in a little bit greater generality. All right. The next thing to talk about is Fermat primes. I'm going to skip that right now, and I'm going to go to Buffon's needle, because I actually did Fermat primes in the past. I can always just give you a link to that. So the way Buffon's needle works is you have a bunch of rods of fixed length, and you have a bunch of parallel lines that have a fixed spacing apart. So here they're using T as the spacing. And you drop the lines, and the question is, how many times do you expect the lines to be crossed by the rods that you drop? The more rods you drop, the more lines you expect. When I was an undergraduate, I asked my probability professor to give a talk in the math club because I was one of the presidents. And before he agreed, he made sure he knew what he was getting into. And he said that, will you guys clean up everything? I said, sure. So he bought a bunch of spaghetti, and he threw the spaghetti up in the air. And so now we can count how often the spaghetti hits the floor tiles and hits the crossing lines. But then he looked at me and said, now let's see what happens if we use wet spaghetti. And he was actually able to get some of the spaghetti to stick on the ceiling. I had to give him credit for that one. So over here, it turns out that there was a great way to do this problem without setting up any integrals. I want to do the long, painful way because it's a great way to talk about joint probability density functions and a great way to talk about how do you attack a problem like this. What do you think happens if I double the length of the rod, which is L, and I double the separation between the planes. How do you think the number of intersections will change? It should be identical. So in some sense, it should only depend on the ratio of L and T. So before we do any calculation, we expect that the answer depends on L over T. Okay, that's a really good statement before we do anything. So when we drop the rod, we have to decide what kind of coordinate system do we want to use. Well, I drop it somewhere in the plane. Without loss of generality, you have complete vertical symmetry. So where does the center of the rod land? What can you tell me about the coordinate where the center lands? Yeah, we just need to know it's left, right. We might as well say that it lands at y equals 0, and we just move it somewhere down here. Right. And so all I really need to know is the center lands somewhere between, say, x equals 0 and t half. And when it lands, I just care about the angle. And I think you can probably argue the angle only has to go from 0 to maybe 90. Right. Of course, if it's over here, you might even be able to do some reflection, but I think we can say between 0 and 90. So I'm going to use, D as my separation. Oh, no, I'll use T. So I have something separated by T. Rod length, I'm going to use a capital L, because I hate lowercase l. It looks too much like a 1. And then the rod center is at 0, x comma 0, where 0 less than equal to x is less than equal to t halves. And then the angle, theta, satisfies when we land. I could land over here at theta equals 0. I could go all the way up to 45. Do I have to go beyond 45? If you want, we can be safe and go all the way up to 90. So let's just go all the way up to 90. It's not worth thinking about it. Whenever you're not sure, let's just say it goes all the way. So 0 less than equal to theta less than equal to pi halves. So I need to have my joint density function. I'm going to use the capital theta. So it's going to be a uniform distribution. I have t halves possibilities for x. I have pi halves possibilities for y. So it should be 1 over t halves times pi halves should be 4 over t pi. Right? And I want to calculate how often the rod can hit. I'm going to assume that L is less than T. If L is less than T, what's the maximum number of times it can hit? So the rod length is less than the distance between the two. It can only hit once unless the rod happens to land perfectly aligned, in which case it hits infinitely often. But the probability of that happening is 0, so we're not going to worry about that. So the rod hits at most once. So it's 0 or one time. Okay. And now we need to calculate how often it hits. And that's going to be a function of the angle and x. So for instance, if x is very close to the middle, if my angle is close to pi halves, I'm not going to hit. And so you can try to calculate, what must your angle be if you're going to hit. So, blowing things up, here is t over 2. And then if I want the rod to just barely hit, let's say the rod lands right over here. So I can try to figure out what this angle is. So by symmetry, if this angle is theta, this angle here is theta. The rod length is going to be L. This distance over here is X. Right? So if I have an angle that is greater than theta, it's no longer going to hit. So anything from 0 up until this is going to hit. And so what is that? So how would you find the critical angle? So given X and L, critical angle theta C satisfies, so what is it going to be? Not arc sine, arc cosine. Satisfies, cosine of theta C equals X over L. So theta C is arc cosine of X over L. So you hit if 0 less than equal to arc cosine X over L. I'm sorry, 0 less than equal to theta less than equal to that. Right? So what do I need to do? So I need to integrate. X goes from 0 to t halves. Theta goes from 0 to arc cosine of X over L. And then for such angles, I get 1. And I have to multiply by the probability density, which is 4 over t pi d theta dx. Okay. Is it hard to do the theta integral? No. I'm sorry? Yeah. So the theta integral is just theta, and then you evaluate it arc cosine X over L from 0. So then you just get, it is the integral, X goes from 0 to t halves of arc cosine of X over L times 4 over t pi dx. And now you have to integrate arc cosine. All right, that integral could be a little bit of a challenge. So I will leave it to you to try to figure out how do you integrate arc cosine. You're welcome to come and visit me in Calc 2 next semester if you wish. You can, of course, use online resources. Or you could say, well, wait, this is a multivariable calculus problem. Maybe I should switch the order of integration. And so try to switch the order of integration. I'll leave that as an exercise. And if you switch the order of integration, I believe it becomes much better. So switch orders. So there are certain questions I am not allowed to ask you. It's your individual personal belief. I cannot ask you any questions on religion. That's inappropriate. What you believe or don't believe is your choice. You have to believe, though, in certain mathematical statistical things. The central limit theorem, for instance, is something that you believe in. There was a class years ago where out of 23 students, 20 got an A plus, 3 got an A. I believe in the central limit theorem. I'm a little suspicious of a grade distribution like that. Paul Erdős, one of the greatest mathematicians of the 20th century, was famous for remarking, you don't have to believe in God, but you have to believe in the book. So the book is a collection of the best proofs of all the results in mathematics. And there is a proof of Buffon's needle without doing any integration. It is an absolutely beautiful proof, where what you do is you take a bunch of rods of small and smaller size and you put them together to make a circle, and you throw down the circle, and the circle diameter is chosen to be exactly equal to t. So no matter how you throw the circle, there's always 2 intersections. It's an absolutely brilliant proof. I will send you the link of just how it is done. And so he said, you're famous that you don't have to believe in God, but you have to believe in the book. He's like, it's those moments in math where you just see something of such great beauty. All right, so this is a good place to stop for today. So there is